So wind classes are defined. Wind is the strength of the wind is classified based on power density at 50 meters above the ground level. So here I've made a chart that shows 50 meters above ground level. And this column is how we define classes. So looking at just this column alone of power density at 50 meters above ground level, a class structure has been invented. And this first row from 0 to 200 power density is called poor. The next one is called marginal. So the strength of the wind is marginal if it yields a power density of 200 to 300. The next one is called fair. Then we have good, excellent. These are actual classifications of wind based on power density. And then it's called outstanding. And what can be better than outstanding? I like this one, superb. So that's literally the class of strength of wind that gives a probability density of 800 to 2000 is called literally superb, or it's called class 7. So the classes have numbers and they have names, but we have to be really careful. We do not say, oh, we have a 7 km/h wind, meters per second wind, therefore the class of wind is excellent. No, what you have to do is this is for reference only. So this is, the velocity is for reference only. What you have to do is you must calculate. You must gather data. You must figure out your distribution. You must find your values of K and A. You must calculate the calculus, which is beyond the scope of this course, so we will not. You cannot just say, oh, the wind atlas says I'm at 7.4, therefore I am in the good wind class and I'm going to put up a wind turbine. No, you have to use an anemometer. You have to collect the wind speed data over time, and then you have to analyze it into the Weibull or the Rayleigh distributions. Find A, find K, and then calculate power density function. Let's look at a bit of an example here. So the annual average wind speed is, I'm into margins again. The annual average wind speed is 7.9 at Conestoga College. Sorry, I can't get out of my the header footer. Okay, the average annual wind speed is 7.9 at Conestoga College. If I measured it 50 meters above ground level. So 50 meter above ground level. So what class is it in? So we don't know how to do the calculus for this question, but let's assume, let's say we have done our good work and we've gone out and we've done some measurements 50 meter above ground level. We got this distribution that looks like a Rayleigh or a Weibull distribution, and then we crunched the data and we said this curve has an A value or a size factor of 8.85 meters per second, and it has a K of of 3. And I don't know if the units really are meters per second here, but that's something that we should look at. And it has a shape factor of K. So this is what of 3 from the Wiley distribution. So now I'm going to do some calculus with this, and I'm going to look at the probability density function as it relates to velocity. Probability density. I'm having troubles in this meeting, aren't I? In this video, probably. Sorry about this. I'm going to look at the probability density function as it relates to V, and I'm going to calculate it. And what I come up with is 424 after all of my magic calculus watts per meter squared beyond the scope of this course to evaluate that equation. So 424 is the probability density. Sorry, I'm going to do the probability density function, and then I'm going to do power. Power density equals from 0 to infinity, constants 1/2 rho, variable V cubed times power density function, V all over dV. And from that, I'm going to get 424 watts per meters squared. So the question is, which class is it in? So I take this 424 and I look at what class it's in. Well, it's 50 meters above ground level. 424 puts us here. Therefore, it is class good. It is class 4. So looking at the chart, it is class 4. Good. The wind is class 4 good in this location. Had I not made this curve, I would have just made a guess, and I would have said, oh, 7.9 takes me here. I am in class 5. Excellent. Then I would have spent a lot of money on a wind turbine installation, but my wind would not have been as powerful as it is, as it actually is, as Weibull distribution proves it is. Therefore, I would have spent too much on the wind turbine, and I would not have been getting enough power out to be able to justify the cost of the wind turbine. So this kind of example, more like illustration, is just meant to illustrate to you that you need to use a Weibull distribution. You need A and K. You need to do the calculus in order to find the right classification of the strength of the wind based on the probability, the correct power density, not based on average velocity that you would get from the wind energy atlas.